20, like 30, 40. So we actually had a we actually have the Efinix FPGA workshop for the basic FPGA concept last week already. So audience for same group of audience, I hope most of them. And so they should have the basic idea of the FPGA, what's going on in the FPGA and the basic concept. So maybe you can focus more on RISC-V architecture in, I don't know, the future applications of FPGA in this talk.
Okay.
I think there are still audience coming in. I suggest we wait for maybe 2-3 more minutes for people to come in so we can start.
Sure.
Okay.
Hey, hello, Ken. Do you have any things to show about the questionnaire or other items?
OK，课程里面所介绍到的这些相关的 data sheet 的话，您都可以在右上角的这个 Efinix 的这个 website 这边，那都可以有相关的这个 data sheet 或者是相关的资讯。那也或者是说，您可以直接。右下角这边的话是我们公司，那不管是您要连接到粉丝专业官方网站或者是 LinkedIn 的部分，那都可以联系到我们。对，那有问题的话也都可以随时跟我们这边联络，这样子。OK。好。
Okay, thank you, Ken. So now we have the most. 30 people in the meeting right now.
Yeah, I think we can start. So, okay. So welcome everyone to this FPGA workshop part 2. And in this today's session, we're very happy to have Wilson online. Wilson is an application engineer from Efinix FPGA company, and he will introduce the RISC-V architecture to us. So I believe that we can learn a lot from this talk. So without taking too much time from me, I will change the control to Wilson. Thank you, Wilson.
Thank you, Professor Lai. So let's get started. So can you see the screen?
Yes.
Okay. So yeah, last week Cam already had the presentation on our FPGA, Trion, Titanium series, and some architectures. So I do not spend much time here in talking about our FPGA game. So maybe if you have interest or if you have any questions or any things you want to know more about us, feel free to drop us email, drop us some message so that we are willing to help and do have some answering your questions. So about our RISC-V hardware architecture. So our solution on the RISC-V FOC is today we will talk about the architecture, the instructions, how to configure our SoC hardware, and some software project development and simulation related. First part is our RISC-V solution called Sapphire SoC. So it is based on the architecture that is the words RISC-V core, which created by the Charles. He is a famous engineer in Europe, developing this RISC-V architecture, and even got some rewards from this architecture. So this core is created from a spindle HDR in Scala. The features of this RISC-V will be as follows. It can support multi-core up to 4 cores. Each core is 32-bit instruction size and data size. We support 6 pipeline stages. We have configurable peripherals such as SPI, I2C, GPIO, interrupt, many other peripherals that we can support. From the benchmark, we can get up to 1.06 DMIPS per megahertz. And we support custom instruction for different users. And our core is Linux compatible. We also provide some Linux resources. User can download and get our board, our development board set up with the RISC-V code together with the Linux support. So it is our SoC architecture for RISC-V. You can see the custom instructions, the MMU, FPU, the instruction, and the data cache inside the main core, which with as suggested in the last page, it is the instruction and the data size is 32 bits. So it's a data bus communicating with the on-chip memory, communicating with the system peripheral bus. Also, we have a dedicated ASI bus for some high-speed external memory connections. So the ASI bus will be connected to, for example, ASI4, we can connect to SDRAM. We can connect to LPDDR4. And also for ASI3, we can connect to HyperRAM, connect to DDR3. So for this ASI bus, we dedicate ASI bus, we want to provide a high-speed connection, and for external memory, which with rather large size compared with the on-chip memory. So main purpose for this peripheral would be for some, for example, data cache, for example, frame buffer for the video applications or some image applications. Or in some streamings, it will add some buff. It will be the buffer for the streamings. And this part will, on the other hand, we have a general system peripheral bus. It is connecting some user peripherals such as GPIO, UART, SPI masters, I2C masters, some timers. Those applications are general for most users in the SoC applications. So, for example, they want to connect to the console for some input and output control interacting with the keyboard or interacting with the PC. They can have some interrupt pin from other sensors or other output device so that we can get some status input from the external device. Of course, for timers, for I2C, we can connect some chips or some memory device, small memory device, so that we can get some instantaneous storage. So we get more about the SoC internal core. Yeah, we at RISC-V core here. So we support multi-CPU, multi-core. So each core we have individual level 1 data cache and instruction cache for each core. While these core will be interact and exchange information through the manager and the local memory bus within the core for the high-speed connection. Then the next stage will be the system main memory bus and the ASI that connects to the external ASI bus and the system peripheral bus as described in the last page. So we can see from this architecture that we want to have a faster data and instruction exchange within the CPU so that we can leverage the different commands and load balancing between each CPU core. It will be more effective using the internal bus instead of exchanging the data and instruction through the external system bus. Of course, all the internal communication are also 32 bits, as suggested. Yeah, for the CPU and the FPU part, we can see the 6 pipeline stage: fetch, injector, decode, execute, memory, and the write back in each CPU core. There are individual pipeline in each CPU. So some of the stage are interacting with the FPU parts. The FPU, we have a single FPU in our architecture. So this depending on the initial configuration, up to 4 CPU core. So these CPU core will share the single FPU within the architecture. So you can see the decode stage sending commands to FPU, and then it will return the data back in the write back stage. While in the write back stage, we also can share the data with the FPU, and then for other instruction, which will be interact with the counters and also the FPU flags. So with this architecture, so each CPU can work independently with different pipeline stage for different commands, individual commands. As well, they can exchange the data, and they can do some cooperation job between different CPU through the FPU commands and the FPU instructions. So it is more effective in this way. So the next part, we will talk about some instruction sets. We are using the RV32I instruction set, which is the basic instruction set for RISC-V 32 bits. Also, we will have some extension support. For example, integer multiplication and division instructions, atomic instructions, and some floating point instruction. It can be single precisions or double precisions. Now, we are going to show how to create the SoC hardware in our device. Yeah, this is the SoC design flow. Most of the FPGA will share a similar design flow, so you can take it for a reference. Even for other vendors, they will share similar things that they have the RTL design. That is the hardware design within the FPGA. We will have this. We have the software, the Efinix software that handle the RTL design, the RISC-V hardware configurations, as well as the integration with the FPGA. So the other part will be the software user will need to develop the software writing in the C or C++ in our embedded software IDE, which is other tools which help to integrate and consolidate all the software compilations, generating the program file available for the bitstream. That is the hardware design to use. So in this case, using these two software, we can develop both the hardware side, hardware connections, hardware configuration of the RISC-V, or even some interaction with other components within the FPGA, not only the RISC-V itself. Then we have the software to control the RISC-V behavior, as well as control everything that connect from connecting to the RISC-V hardware. So it is the complete design flow from Efinity. So we create the project for our target FPGA, and then start a RISC-V IP and generate the RISC-V with our configurations and also other IP if you need. For example, you need the DDR support, DDR memory support, so you can generate the DDR IP, or maybe you have some functions you need to use in your design. You can generate that functions, some calculation module or image processor module, and then combine it in the Efinity software. So you have a complete project for the FPGA. Then the next part will be the software and the hardware development. For the software development, you create a project with the IDE inside the SDK, that is the IDE, coding the C or C++ program for the RISC-V, and then compile it. And at the same time, for the hardware, we have the core for the RISC-V and other IP. Then we integrate it in the hardware. Also assign the pin, the function of the pin in the FPGA, connecting all these modules, and doing the FPGA the program for the FPGA hardware. So now we have the FPGA hardware program and also the software for the RISC-V. The last part will be integration, integrating the hardware and software. So now we combine the bitstream that is from the FPGA hardware and also the RISC-V software into a single program. Now we copy the program on our hardware. There is the maybe our development board, or user create their own board for the hardware verification. Now we test the boot up and check the functions of the software, whether it behave like as we expect in our design. So after the verification, then okay, everything is. If there is any issue, of course, we need to go back for the software or other hardware debugging. Otherwise, if all the function performs as expected, the development cycle is complete, and we can have a functional hardware with RISC-V and the software for the for our applications. Now it is the step to create the Efinity project on how to create the RISC-V project one by one. First, we create the Efinity project, and we open the Efinity software, and then create the project on our target device. Then we can start a new SoC. In the SoC, we have a lot of configuration available. For example, number of CPU core, you can link up with our architecture on that part. core frequency. Yeah, we need to supply the clock to the FPGA, of course. Sorry, to the SoC, of course, to in order for the function, for all the functions and the operations. And we have the choice to use separate peripheral clocks. By default, the peripheral are sharing the same clock as the core component, but we also have the options to use separate peripheral clock. We enable the data instructions cache. It is by default on. So if we do not enable it, it will be a CPU call without any data or instruction cache. So we are allowed to enable some custom instruction interface. We have the memory management unit for virtual memory. That is a requirement for the Linux operation. So if we are using Linux, we need to enable it. As suggested in the previous page, we support the floating point instruction set as extension. So we can take it here to enable the floating point instructions. Also, another extension instruction set, the atomic instruction, we can enable here. So we have the cache options. The cache, there are some different options for the data cache and the instruction cache. So it can up to from 1 to 8 way and up to 32 kbytes. Now our core can communicate through the AXI bus with to the external memory. So we can enable it here. Now we can have the AXI memory for LPDDR4 or AXI3 for the DDR3, LPDDR2. And we can also place the software in the external memory in this case. So we specify the memory data width and the memory address size. Of course, we also we need to have the on-chip memory for the startup for the bootloader. So we can enable the on-chip RAM size up to 512 kbytes. So if you have some customized chip applications, so you can also override the bootloader for the applications. Yeah, since we do not expect our software or even the hardware can run without any issue after the first compilation, so we provide a way to debug. We provide the debugger for the connections to monitor the situation within the SoC. So we have a standalone connection on the debugger or even daisy chain connection on the debugger. We by default we use the FPGA contains a hardware JTAG port, but if it has been used for other purpose, we can also assign the GPIO as the soft JTAG. We also specify the JTAG FPGA port for that debugger purpose. Yeah, for the settings below, it is targeting for different device, the applications region size, the stack size, for the debugging purpose. So the next part will be the peripheral configurations. Now we have different peripheral here: UART, SPI, I2C, GPIO, APB3, ASI4 configuration, some user interrupt or user timer. So the configuration for those items are quite similar. You can enable it, assign the interrupt ID for the corresponding peripheral, and then some of the parts will be must required together with the generation, but some of them are free to choose. Maybe you can enable one or enable two of them, or even that you do not enable any of the peripheral. But by default, the UART0 must be required, since we need at least one communication method towards the SoC, so that we can monitor the status and we can get some operation with it. The next part will be the base address configuration. So we have the on-chip RAM, we have the external memory, and we have the peripheral. By default, we can allow the software to assign all the address automatically. But in some cases, maybe your software has some specific action, or some of the external memory will be used to store other information, for example, frame buffer, for example, some data storage in your calculation. So you do not want to start the memory access from the SoC on that particular address position. So you can choose the custom settings, and then change the address on your own to fit your applications. Now we got every SoC settings available. So the next step will be generate the SoC in the hardware. Now we get the settings, generate it, and then we can find a lot of files within our project. Some RAM configurations files, some Verilog file that we later on need to use them to integrate with our other modules. Also, we provide some example design that is a complete simple design with all the hardware, and also some demo software within the project, so that you can if you just want to try to run some SoC on our development board, you can just pick up these example projects and then use them together with the software embedded to have a simple test on the development board. And understand, it helps you understand how the device is run, how the software is run, or even how we can communicate or combine the hardware and the software using this example design. So for the memory address, we can have a more clear picture about that. By default, we have the start address as all 0. And then reserving some for the bootloader, and then we have the external memory address size. Then starting from another base address, we will have the address gap around 16 megabytes in between different regions. We have 3 regions: external memory, ASI, that is for the peripheral, and also for the I/O on-chip RAM, it will be another section, 3 different sections. So each will have a address gap to separate them. make sure they do not overlap to one another. So the second starting address for the A-side slave part. And then the last one will be the starting address for the I/O and also for the on-chip memory. So in your software, you are accessing these addresses location for your data, memory arrangement, memory assignment, or even you are accessing the I/O for different address. We have the mapping according to our ID, so that you can in previous page you can see the start address for the UARTs, for the SPI, for the I2C, etc. So when you visit this address in your software, you can control the output or read the input value coming from this peripheral device. So details for the I/O space memory. This is the starting address, starting peripheral address. This is just the offset one. So the base address is here. Is example base address, F8 and followed by 60. Then starting from that address, base address, we have the offset 0 address for the peripheral space. There's the timer, SPI, I2C, etc. Then we will have the custom logic space. So we have the APB3 device, APB3 bus to connect to some custom device. We will take this region for these device access. Now the last part will be PLIC access. So the total size of these I/O memory space will be 16 megabytes large. Okay. Is there any questions about the memory locations or the architecture of our SoC device? Let's continue the second part of the training session. Now, we discussed the hardware architecture, how to create a hardware in the first half. So in the second half, we will more focus on the software project itself. Now we have the hardware on hand, how we can control the SoC, how we can get the software ready for the SoC so that it can boot up and run the application that we want. Yeah, we have the software IDE available for the software development. So first of all, you need to install it and then launch the software IDE, and then choose the folder for your project workspace. And yeah, there are several types of project that you can use, but a very simple one will be importing from existing code. So you already have some project from, maybe you download it from some website, from some, for example, GitHub, GitLab, or even you get some old project that is for other platform. You want to port it to our project. So you can import existing code using the method, and then find the make file. It should already get the make file ready with the existing project. So you assign it, assign the folder to the settings, and then you will get you will get the project on the programming platform in this software IDE platform. So the next step is you need to do is to right-click the project and then build the project with the file you already have. So after completely building the project, you will get some files in the Project Explorer. There are some files that you can use to run in the SoC. For example, for the .bin file, it is for the SPI flash programming purpose. It will combine with our hardware bitstream prepared in the previous steps and generate the bitstream to program to the flash device on your user hardware board and run the hardware together with the software. And also there is a .elf file. This file is for the open OCD debug purpose. So in the last sessions, we talked about enabling debugger to check the software status. So in this case, you do not need the .bin file. Instead, you open our interface, open our IDE interface, and use this .elf file to program into our SoC hardware, and then run this ad hoc. And then you can do some debugging, checking, etc. Check the status. So how to work on the hardware debug? Now it will be rather simple. First, you import the launch configuration. Then in the configuration windows, you select the config of your hardware SoC. There are a few different types of debug methods available. So it's a soft tape launch for the as suggested in the first page, we have two type of devices, the Trion and Titanium. So this default underscore TI is for the Titanium devices, while the default .launch file is for the Trion devices. So once you get the configuration of your SoC, then you click finish to complete. Now you have the ELF file in the compilation. You get the ELF file from the compilation. You use the debug as the function, right click and get the debug as function, and you call the debug configuration windows. Now you specify the project name, the application file, that is the .elf file, and then choose which type of debug method you need to you are going to use. For example, for Trion hard JTAG tape project, using the Trion Trion Titanium soft JTAG tape project, and also for the Titanium hard JTAG tape project. So you can choose which type of application you are, and then start the debugging. So the last part of today's training will be the software simulation. So maybe you do not have the hardware on hand every time. Sometimes you already have the hardware, you already build everything for the SoC, and then you want to test your software on board. This is the most precise way and the efficient way to do so. But sometimes you only have a software application that you just want to try on the SoC to see whether it works or not, or you just want to estimate some functions. So you can use the QMIL emulator provided in our IDE tools for the debugging, for the emulation purpose. So why choosing QMIL? It is generic and it is open source emulator. So it already supports the RISC-V architecture emulation. Now we provide a bare metal RISC-V package under the model SPITE for the software simulation purpose. So you can get the zip package, the RISC-V package here. Then what is SPITE simulator? So it is a function simulator. In actual compilation or running your hardware, you will have something like memory transactions, some IOSS, or even your cache data cache instruction cache may get some cache or miss instructions there. So in this model, it just ignore all this delay. So it just simulate the functions of your program. And also, though it doesn't have a cache for the data, it just trace or monitor. It just provides some space for you to check the register value or the data value at some point, but it didn't catch or it didn't store all the data within the process. So it is also a multi-core framework. It has a MMU in each core. But it will be some different structure architecture compared with our hardware. You can see they have a common instruction and the data cache instead of a separate one for each processor. And it also have L2 cache, level 2 cache. So, but of course, since it is just a functional simulator, what we want to is to check the functionality of our software code, not the exact performance or what is this behavior in the hardware. In that case, we also provide some hardware simulation purpose, working with our hardware, but it will be more complicated, so I will not cover it today. But anyone, if you are interested, just maybe you can send us some message or email so that we can provide more information about that part for you. Or of course, actually, our user manual in our website already suggests all the methods, including the software simulation, the software plus hardware simulation, and also, of course, the hardware debugging testing purpose. So you can go to our website, download the documentation, and check all these methods. So when we run the QMIL, want to run the QMIL simulation, we get the file, we get the existing project from the workspace and select the archive file. That is this file in our IDE. So you can get the project here. The next step is there are already some C codes included in the package. So if you just want to try it, you can just make use of the example C code inside the source folder and build the project and start the and run the debug as, similar to the hardware debugging. It is a single step debug as, debug configuration, and then start the debug purpose. But if you want to use your own project, then you will replace the code within the source folder and rebuild the project. How to rebuild? You can just replace the project, refresh this folder, and then choose clean the project to clean out any previous compilation result and build the project again. So then the last step, of course, is run the debug as, debug configuration to start the debug process. So you will go to the simulation debug interface. Is common for the hardware and the software. So I'll put this here. So in this interface, you can see the stack information here. Different thread, the current position of the stack, and you can see the source code associated that is running on the CPU, and you can check the console output if you have any. You already connect you already have the standard I/O connected to the source code, so you may see some console output here. Also, you click this button to show the instructions in the stepping mode. Now, once you click it, you can see this is the window for the variables, breakpoint, and the instructions. So once you click it, start running the debugging, and then you can see all the instructions here. Is the assembly code that is running on the CPU, on that particular CPU. You can check which instruction is highlighted, which is the latest instruction running, and which corresponding to the source code, the C code that you write. So it helps you to debug. Oh, okay. Once you have something that got stuck in your program, you can check. Okay, which instruction is this running? The value of the variable breakpoint and some expressions, and also the stack, whether it's already full or which status, which location is accessing. So it helps you to debug the software in while running in the SoC. Also, you can also check the number of instructions counts by going through these parameters. We provide some reference value there. So for more information, we have the hardware user guide in our support portal, in our website. The QMU documentation here, which you can see some more operation or more type of models available for the QMU. It doesn't it has a lot of model, even some Linux or Windows compilation for the QMU. So it doesn't only available for the RISC-V architecture. Of course, it contains many different RISC-V architecture. For example, some maybe contains peripheral, some maybe even contain some memory support. So a lot of different type of emulation. So you can check the document for more how to generate different kinds of emulation model. So it is a quick introduction on the SPIKE model, which I adapt in this training. Okay, this is the end of today's presentation. Any questions? Yeah, I will send today's presentation material to professors so that he can share it to the teams, to all the students. If you have any questions or if you are interested in getting more information on our device, on our SoC, or even our software, so feel free to contact us at any time through email, through we have a forum in our website so that you can ask some questions. Our team members and also some volunteers are willing to help you to understand more on our hardware, or even you have some question on the RISC-V running in our hardware. So we are willing to help.
Yeah, thank you, Wilson.
Yes, thank you.
Yeah, today I think we really learned a lot because I think most of the audience are the current students in the computer organization class.
Mhm.
So we actually just finished the discussion about the pipeline stages.
Mhm.
So I think they can, really feel what you are talking about, what you're trying to tell them. I think this is very interesting.
Mhm.
And yeah, I will share the materials, including your slides and maybe the video recording. I'm not sure.
Yeah, okay.
I'll share that on the class website so students can just follow up.
Sure.
And if they have any further questions or interests to know more, or maybe try to actually use the Efinix board, so who should they contact? Is that you or some other contact window?
Oh, maybe in this case, if there is some question from the student, you can contact Ken first. Ken will communicate with
Oh,
me
okay.
on the questions. Of course, our website has free access. You can just register the account on our website, and then you can access most of the applications here. Even now, our software is now free for the license. So if any student is interested in testing our software or using the IDE, they can register an account in our website, and then we can provide the software to them.
Okay, so what if they want to get the board, the FPGA board, so they can contact Ken, right?
Yeah, they can contact Ken
Okay,
first, and
okay.
then we can
Yes.
organize. We can discuss how to organize more boards for the students.
Okay. All right, great. So, is there any questions from the audience?
Hello.
Yes.
Okay,
Quick question. Hey, so for my understanding that if we want to test the performance of our the simulation for the software, we should use the spike. We need to run the spike by ourselves. Is it true?
Yes. Actually, for the software simulation, this part, different models may have different applications. So one of the way is to actually run the simulation on the IDE software. There are depending on which kind of performance that you want to measure, that you want to check. Maybe there is also some benchmarking application available in the website, in the web, so that you can download those benchmark and then run within the SPI model or within your software, so for more checking. So there are more than one way to check the performance. Yeah,
I think Chire is asking, if you run the QEMU, there won't be any performance numbers for processor. But since you called the Spike is a cache simulator, Spike will give you some numbers like hit rate, miss rate, or number of accesses. These kind of these are considered like cache performance. So the Spike tool is already integrated with the QEMU environment. I mean, you're in this case. So when we use your IDE, uses QEMU interface, when we run the program, then we will be able to get the Spike number out. Get the cache performance, let's say, cache performance. Like how many hits, how many total access, how many hits, how many miss, and what's the latency? No, not the latency, but at least to get the miss and hits.
Yes, understand this point. In theory, it should get the data that you want. For example, to catch hit and miss information. But at this moment, we are it is our we are still discussing some plans to improve our environment to display more information for the software simulation. So that's why I didn't include everything here, since some of them are still in discussion in the future software release to include more information about the software simulation. For hardware simulation or hardware plus software simulation, we can get more information from that.
Okay. Thank you.
Yeah. Yeah, thank you for your question. It is inspiring. Actually, we also wants to get more comments from all the users to improve our software, to include more. Let's say for the software simulation, we want to include more information on that, so that user can check it without using the hardware every time.
I think there's speaking of which kind of design environment, I have a suggestion that since you are integrating RISC-V in there, and everything, and you will not only just have the RISC-V, you probably will have some coprocessor or I don't know, accelerator next to it, talking to each other. Maybe it's a good idea that the next step in the future work, they can construct a kind of complete virtual platform, including the RISC-V and maybe the accelerator part that users can write some high-level models, like in C, C++, to just simulate the functions. And the tools can take the whole into account and quickly return kind of a feedback about what's the approximate resource usage. It is too big, cannot be fitted into the FPGA, or would that be where the bottleneck is going to be, for example. I mean, so user doesn't need to jump into the real hardware to the board level design or testing or verification, because that will take much more time. So if you can have the virtual platform for user to play with, I think this will be pretty useful, convenient for users to adopt this kind of system.
Yeah. Thank you for the comments. So I'll bring the information to the software team and try to discuss whether maybe we can actually build up a virtual platform for more information include, so that the users or students or even some customers, they can make use of them in their development. Yeah, thank you.
Okay, so
Okay.
do we have more questions? Or I don't know, for the platform, maybe for, I don't know, for the company, if students want to know more about Efinix. Okay. I think if no, I will thank Wilson again for the wonderful, very helpful and informative speech today. We really learned a lot. So thank you very much, Wilson.
Thank you, Professor.
Okay, I think that will conclude the workshop today. Thank you very much, everybody, for your joining. Thanks. Bye-bye.
Thank you for joining
Bye.
the training. Bye bye.